That's the end of work, power and energy. This section is about electromagnetic effects. Electricity, magnetism and movement are all linked. First, let's remind ourselves about the properties of magnets. As you watch the next clip, note down some of the properties of magnets and magnetic fields.
A magnet doesn't have to be touching whatever it's attracting, like this paper clip. The force of the magnet can be sensed all around the magnet, and this space of attraction is called the magnetic field. Now, the magnetic field is invisible to our eyes, so how do we see it? Well, these small pieces of iron are called iron filings, and they line up in the shape of the magnetic field. And where the lines are closest is where the force is strongest, at the ends of the magnet, at the poles. This is only part of the picture. Magnetic force doesn't just work in air. The iron filings have been mixed with oil. Drop in the magnet, we can see the shape of the magnetic field all around the magnet. The iron filings are closest together at the poles, and that's where the magnetic field is strongest. Further away from the magnet, the filings are wider apart, and that shows that the magnetic force decreases the further away you are from a magnet.
We saw that magnets can exert a force on magnetic materials without touching them, so magnetism is a field force, not a contact force. The area around a magnet where the magnetic force acts is called a magnetic field. Lines of force point away from the North Pole towards the South Pole. Lines of force are closer together where the field is stronger and further apart where the field is weaker. Opposite poles attract each other, while like poles repel each other. So, what's the link between magnetism and electricity? As you watch the next clip, work out what's happening.
The battery makes a small current that lights up a bulb, but the current also makes a magnetic field. It's just strong enough to push the needle on this compass, but only just. This battery is a lot bigger. Although it makes about the same voltage, it can send a much bigger current down this wire to work the van's starter motor. Even so, the magnetic field made by the big current is only just strong enough to push these iron filings into line.
When a current passes through the wire, it produces a magnetic field around the wire. This is called the electromagnetic effect. When the current flows in one direction, a magnetic field circles around the wire in one direction. When the current is reversed, the magnetic field circles around the wire in the other direction. When the current is switched off, the magnetic field stops. This can cause practical problems. Can you think of places where electrical cables might pass close to magnets?
Tally-ho, pass me the good old compass. So where's the problem?
Well, Harry, the problem is in these instruments here that are all electrical, and the electrical current that goes through the cable gives off a magnetic field that deflects the compass.
Well, I can't detect anything.
You can't detect it because none of this is turned on. Look.
Ah. Oh, yes. I can see it now. So why can't we insulate against that?
Well, you can insulate the cables against electricity from leaking, but you can't insulate the cables from magnetic fields.
So how do you correct a compass that's pointing in the wrong direction?
Well, that's easy, Harry. What we use are permanent magnets like these, and we put them around the compass to deflect the compass card back to its true position.
So pull it round?
That's right, yes.
So let's say, for the sake of argument, nick your magnet, that this is an electrical cable producing a magnetic field, and it's pulling the compass round.
OK, I'll take another magnet, and I'll put it on the other side and allow it to pull it back to its true heading.
That's clever.
So the magnetic field created by a current flowing through an electrical cable can interfere with plane and also ship's compasses unless it's corrected. Another example is when the magnetic field around an electrical cable causes a humming sound in a loudspeaker. This electromagnetic effect can be put to good use to make an electromagnet. If the wire is made into a coil, the current flowing through it creates a magnetic field that is the same as around a bar magnet. It's an electric magnet. When the current is switched off, the magnetic field disappears. A coiled wire like this is called a solenoid. Can you think of ways of increasing the strength of the magnetic field in the coil?
Let me see. Right, it says here that I can increase the strength of the magnetic field by wrapping the wire into a coil. Well, I've done that. Magnetic field's not strong enough. You can increase the magnetic field by putting something into the coil. Plastic. Well, that's not really effective. What about this? Iron. Now that's better, but it's still not strong enough.
Now, another way to increase the strength of the magnetic field is to use more than one coil, and bringing the ends together is even better. It's certainly having some effect, but there's still room for improvement.
A larger electrical current through the coils. Can't do that. Larger coils. Can do that. So, now I've got a magnet that I can switch on and off as needed.
So the strength of the magnetic field in the coil can be increased by increasing the number of turns in the coil, increasing the flow of current, or placing a soft iron rod or core inside the coil. Soft iron is used for the core because it becomes magnetic as soon as the current is switched on, and loses its magnetic effect as soon as the current is switched off. A magnet that can be turned on and off like this is called an electromagnet. Watch the next clip carefully for another explanation of how they work.
Electromagnets are really just coils of wire. It's easiest to see how one works away from the machine. Put a steel plunger inside the coil, then pass a current through the coil and the plunger gets pulled in magnetically. It takes very little current to do this because the hundreds of turns of wire magnify the magnetic effect strongly. The magnetic field from one turn of wire is weak, but add more turns and now there are many wires side by side, each carrying the same current in the same direction. So there's many times the magnetic field. The more turns, the stronger the field.
Here's a circuit diagram of an electric bell. When the current flows in the circuit, it passes through the coil of an electromagnet. The bell hammer is attached to a piece of springy metal, which is part of the circuit. Have a go at explaining exactly how the electric bell works. If you get a question like this, you need to explain exactly what happens, in the correct order. Something like this. When the current is switched on, it flows in the wire coil. That creates a magnetic force which attracts the bell hammer and clangs the bell. It also breaks the circuit, which turns off the electromagnet and releases the hammer so it springs back into its original position. That turns the current on again, which turns on the electromagnet, and so on, very quickly. This is what you might have written. Another useful application of an electromagnet is in a relay. A relay is a switch that's operated by an electromagnet. They're often used for safety reasons to operate switches at a distance from the operator. They can also use a small current to control a large current. When a small current flows in the relay, it activates the electromagnet. That pulls the large switch closed, which lets a larger current flow into the other circuit. When the small current in the relay is switched off, it releases the electromagnet. That opens the large switch, which stops the larger current. Even if you don't get a bell or a relay in your exam, knowing how they work should help you deal with any other questions about electromagnets in action. There's more about electromagnetic effects in the physics section of the higher tier science programme.